Alright, hello and welcome everybody to the first video of the quarter. Um, this is Business Calculus, Math 148, and essentially calculus is concerned with studying what are called rates of change, how things change over time. And so we'll be learning the calculus this quarter, and as well we're going to be looking at as many business applications to calculus as we can. The first chapter might do you some good to go through that if you want to. Chapter 1 is essentially algebra review or pre-calculus review. I will be reviewing pre-calculus as I'm teaching calculus as much as I can in these videos. So I'm going to start by skipping to the first section that actually deals with any calculus, section 2.1. This is entitled An Introduction to what are called limits. And limits, for some of you, the concept of a limit might not necessarily be new. For some of you, it may as well be, or it may be new, or you might be seeing this for the first time. Okay, so ultimately, like I was saying earlier, calculus is the study of rates of change, and an object or function that calculates a rate of change for you is something called the derivative, which we will be learning about at the end of this section, at the end of this chapter, and in the next chapter. The derivative is a function that gives you those rates of change. It's mainly the focus of this class. It's going to be, the majority of this class is going to be spent on derivatives. The rest of the class is going to be spent by doing something called anti-differentiation or integration. Okay, so let's get started with limits. Okay, so 2.1, this handout is also posted. If you're watching the video right now, you would have gone in the Canvas module, clicked on the video assignment, which has no points attached to it. It's just an assignment to give you a deadline just to keep you on track. But when you clicked on that video or opened that video, there should also have been a link for you to click on that opens this handout if you do want to, for whatever reason, print it or look back and see what examples I covered. You can do that as well. It also summarizes some key definitions, and other facts that we will use throughout the quarter, formulas, etc. Okay, so what is a limit? So I'll talk about notation for a second, kind of give you an idea. Now, a lot of you might be familiar with the notion of what are called asymptotes, vertical and horizontal. Some of you might be familiar with the notion of end behavior, and a limit is something that can basically contain all the information you want to know about asymptotes or end behavior, but you can also, limits can do a little bit more for you, and we're going to see later on that a limit is needed to find a derivative of a function. Okay, so this is something we're going to need later on. Okay, so now the definition of a limit is, I'll have you focus on this part down here. Okay, so this is the notation that we're going to use, and the way that this is read is this is the limit of the function f of x as x approaches a. Okay, so when I say this, when I write this down, I'm saying this is the limit of f of x. And essentially, f of x is a function value. We'll talk about functions in just a second. You should have some familiar notion of functions from pre-calculus class. So what this is again, this is the limit of f of x as x. This arrow stands for approaching. So you're saying the independent variable x is approaching some value a, which is either going to be some number, or we will look at end behavior of functions, so we want to know what happens to the outputs, or the f of x values. Okay, so these are the outputs of the function. And basically what we're saying is, what are these outputs approaching as the inputs x get close to a value a? And then what you will say is that if there's a number L, so that f of x approaches L as x approaches a, okay, we're going to say that the limit of f of x as x approaches a equals L. Okay, and I'll be able to show you some algebraic examples, some graphical examples, and as well as just to do some kind of heuristic investigation making tables. Okay, so again, the main idea here is, and you can read underneath what it says in words, you write the limit of f of x as x approaches a equals L if the values of f of x get close to a specific value L for values of x that are approaching a but not equal to a from either side. If a limit L exists, it is unique, so a function cannot have more than one limit. So there are times where limits of a function at a particular value, at a particular x value, do not exist. Okay, and there are times, okay, where a limit does exist and equals some number. Okay, and again, all a limit is really the behavior of a function for some value that's not necessarily in your domain, but something that the values of x approach. Okay, that's what a is. So a is some number. It's not necessarily in the domain, but values x in the domain have to approach that a value. And you look at all the corresponding output values f of x, and if they seem to be getting close to a number L, that becomes the limit. Okay, so for example 1, just to give you an idea of how this works, and I'll again do this graphically, talk about this graphically, algebraically, so on and so forth. Okay. So first I'm going to look graphically. And maybe I'll remind or refresh you on some algebra here as I get started. So I'm going to do a few things. First is I'm going to look at the function f of x, okay, which is 2x squared minus 9x plus 9 over x minus 3. Okay. Now, what you'll notice here is that x cannot equal 3. Okay, so basically what I'm going to be doing right now is finding the domain. The domain is the set of all x values so that the output is a real number. In a quotient of polynomials, 2x squared minus 9x plus 9, whose domain is all real numbers, over x minus 3, also a polynomial, the domain of this function is everything except every x value except for ones that make the denominator 0, which only happens at 3. Okay, so what I might say is the domain, oftentimes here's how you're going to see this written in the textbook, it's negative infinity to 3 union 3 to infinity. So that would be the interval notation for the set of all numbers excluding positive 3. Okay. So that just means that this function does not have a point that corresponds to x equals 3, but it's defined everywhere else. Now, a little bit of a review here is this function can actually be simplified a little bit. If you look on the left, you'll notice that I have this function graphed, and the graph looks like it's a line. It is going to become a linear function, and you'll see that after I simplify by factoring the numerator. Okay. So I'll get to the question in just a second. You have this rational function, and if I read the question, is there a number L that f of x approaches as x approaches or gets close to positive 3? So again, if this is basically saying, is there a limit at 3? Notice 3 is not in the domain of the function. Okay, but it's the only number not in the domain, so we can still have numbers in the domain that get close to 3 but never quite get there. As you plug those numbers into the function f of x, okay, do the outputs approach some particular value as the inputs approach 3? Okay, now back to this again. I'm just going to simplify this function. This is going to explain to you why the graph looks like a line. The numerator can actually be factored into a product of binomials. Denominator would just still be x minus 3. And you might have to do some guessing and checking. If the numerator is going to factor, in each of those two factors that I've just written, one has to begin with 2x and the other has to begin with x, so that they would multiply to 2x squared. Okay, now I'm just going to do a guess method here. If you look at the numerator, okay, the constant term is 9. Okay, and I have to split up those factors as well. And I'm just going to guess, I believe it's got to be 3 and 3. Okay, the only factors of 9 are 1 and 9 and 3 and 3. Okay. And think about, again, if you FOIL the resulting binomial factors, the first term has to be 2x squared and the last term has to be positive 9. Okay. And then I believe if you look at the middle term, it's minus 9x. Okay. I believe that both of those values have to be negative 3 and negative 3. They multiply to positive 9, but the inner terms multiply to negative 3x. The outer terms, excuse me, let me redo some of this. These outer terms multiply to negative 6x, and negative 6x minus 3x gives me the middle term of minus 9x. And then finally, you'll notice that the numerator now has a factor of x minus 3. So f of x, after simplifying, is just equal to 2x minus 3. Okay, but remember, that was simplified, and you have to remember that x is not allowed to be positive 3. If you look at the graph, that is why we have that open circle right there. Okay, so basically this rational function, it simplifies to a linear function. That's why its graph is a line. But because there was a factor of x minus 3 gotten rid of on top and bottom, that leads to a hole at x equals 3. Okay, so just a little bit of algebra review, some factoring, thinking about the graph. Now I want to actually answer this question of a limit. Okay, so again, focusing on, this question up here. Is there a number L that f of x approaches as x approaches or gets close to 3? Okay, so I'm going to do this graphically first. Okay, so another way to ask this question is, does f have a limit L at x equals 3? Okay, now when I do this graphically, one thing I like to do is just draw, this is hard for me to do on my stylus pen, but I would just draw a vertical line. Okay, this is the line x equals 3. So that's where I want to know if there's a limit. Okay, now I want you to look at the x-axis. You're going to think about x values getting close to 3, and think about what the outputs, right? The f of x values are just the y coordinates. And if you look at the y-axis now, right, if I approach 3 from the left, notice what the y values are doing. They're approaching positive 3. Let me get rid of this for a second. Now if I approach 3 from the right, Okay, again, you have to be able to approach the function values, or the y-coordinates have to approach the same value from both sides. Okay, well, if you approach 3 from the right, notice what's happening to the y-coordinates. Okay, they're approaching the y-coordinate of positive 3. Okay, if we focus on this y-coordinate right here. You can also see this on the graph. If you just follow the graph on both sides, right, the graphs are both approaching the same point, and that point has a y-coordinate of positive 3. Okay, so again, if you think about approaching your x-coordinate on the left or the right, and you follow what's happening on the graph, as you approach 3, if x approaches 3 on the left side, you'll notice that the function values are increasing and approaching 3 from the left. If you approach x equals 3 from the right-hand side on the x-axis, and you go up to the graph, you'll notice that you will be approaching positive 3 from above. And since this is why I've drawn this vertical dashed line, notice that the function or the graph seems to be approaching the same point on this line. So the answer would be yes. Okay, this function does have a limit L at x equals 3, and then notationally this would be, okay, the limit as x approaches 3 of the function f of x is equal to positive 3. Okay, because that's what the y-coordinates are approaching as the inputs x approach 3. So again, think about whatever you're wondering whether you have a limit at. Okay, if you have a limit at a place on the x-axis, in this case 3, as you approach 3 on the right or left side on the x-axis, think about what the graph is doing. If the graph is approaching the same point on the left and right side of that vertical line, okay, the y-coordinate of that common point that you are approaching is the limit. Okay. Eventually we're going to see an example of when there is not a limit at a particular value. Now, again, the reason I wanted to do this particular example is, notice f of 3 does not exist because 3 is not in the domain, but you still have a limit at 3, and that limit is 3. So a limit can exist when a function fails to exist. A limit can exist at a value that is not in the domain of the original function. Okay. So now, if you wanted to do some of this numerically, I've just made some tables. And again, for a limit to exist, you have to approach that x value from both the left and right hand side, and the graph would have to approach the same point, or the f of x, the y-coordinates would have to approach the same value for there to be a limit, as we saw was 3. Okay, so there's something called a left-hand limit. This is where you approach your x-coordinate from the left. I have just made a table of values here. Okay. So basically what I have in this table is on the left-hand side, that is the x value. And on the right-hand side, that's the value of 2x minus 3. Okay, so remember, f of x, which was 2x squared minus 9x plus 9 over x minus 3, just simplified to 2x minus 3. Okay, and you just have to remember that 3 is not in the domain. So when you plug in 2.9, you'll see that you'll get 2.8. When you plug 2.91 in, you'll get 2.82. And what you're going to notice here is that as you increase from 2.9, if you're looking on the left, as x increases from 2.9 to 2.99, okay, these are the f of x values. And you'll notice that they're growing. So if you approach 3 from the left, the function values are increasing to the value that is seemingly 3. Right? 2.8, 2.82. You know, by the time x is 2.99, you get 2.98. Okay. If you could also try to usually what I would do if I make a table, let me show you, is I would probably, if I'm doing a left-hand limit and I'm just inspecting it through a table, I would probably just go with 2.9, 2.99, 2.999. You'll see that when you plug 2.9 in, you'll get 2.8. When you plug 2.99 in, you get 2.98. And I believe, you'll have to double check this one, I think this is the pattern, is the outputs are just gonna, you're just gonna be, every time you add a 9 to the decimal place on X, you're gonna add an extra 9 between the decimal and the 8 in the output. Right, so for instance, if X was if there was 4 nines after the decimal, notice these values are getting close to 3. Right, just by adding a 9 after the decimal place, I'm making my X values approach 3 from the left. And you'll notice that when you slip an extra 9 between 8 and the decimal, those function values are getting closer and closer to 3. Okay. So again, you can find a limit graphically, or you can make a table. But if you're going to make tables, you have to do from the left-hand side, so you have to approach 3 with numbers that are getting larger as you get close to 3. Or you can also do a right-hand limit. And again, I'll just make a table. You know, I usually would make a table like this. And notice now the X values are going to get close to 3, but this time from the right. So right, I'm starting at 3.1 and 3.09. This is me decreasing the hundredths place by 1 each time. But usually if I was going to do this by hand, I'd probably start with, say, maybe 3.1, and then I would just put an extra 0 between the decimal place and the 1. So now notice what are those X values doing? They are getting close to 3, but they are decreasing. So I'm approaching from the right-hand side. The function values are 3.2, 3.02. If you plug in 3.001, you're going to notice you get 3.002, and when you plug in 3.0001, you're going to notice that f of x is 3.0002. Okay, so again, you'll notice that as x approaches 3, this time from the right, the f of x values are also approaching, or getting closer to positive 3 each time. And since you have the same behavior on both sides, I would say that the behavior, or the limit of f of x as x approaches 3, the outputs are getting closer and closer to positive 3. And remember, again, the function does not exist. Oops. The function does not exist at 3, even though the limit does. Okay. There are also times... There are times, though, where a function does exist, but the limit does not. Okay, we'll investigate some of this stuff later. Okay. Now, there is an algebraic component to calculating a limit. I guess I can give you a little bit of a preview of that. Like, it does turn out... If I was doing the limit of the function in algebraic, right, I can write that algebraic expression in. So what does 2x squared minus 9x plus 9 over x minus 3 get close to as x approaches 3? We're going to see here in just a second that since I'm approaching 3, but I'm never getting there, again, we can't get to, this expression can never be defined at 3. So, right, when you look down here, when I say x is approaching 3, I mean it's getting close, but never quite getting there. Since x is never going to be 3, I can simplify the function I'm finding the limit of. That does simplify to 2x minus 3 as long as x is not equal to 3. And we're going to see eventually it does end up being true that a limit of a polynomial is you just have to plug the limiting value in for x. Okay, so I'll just plug in 3 for x, because 2x minus 3 is a polynomial. 2 times 3 is 6, minus 3 gives me the same limit of positive 3. So there's really 3 ways to do a limit. Well, there might be even 4 ways, but you can do it graphically. You can do it numerically by just plugging in values into the function that get closer to, in this case, 3. Or for certain functions, you can do it algebraically, where you simplify the function until a point where you can just plug the what I call the limiting value. I'm going to circle it in purple. Right, so you simplify the function to a point where you can plug this limiting value into the function to calculate the limit. Okay, so and notice you were not able to plug in 3 until you simplified or canceled that x minus 3 factor in the denominator. Okay, now what you just saw was an example of what are called one-sided limits. Okay, so there's a left-hand limit and a right-hand limit. Now, what you're going to notice right here with the left-hand limits, I'll box that first. I would say that the limit of f of x equals L as x approaches a from the left. This just means that as you approach a from values that are less than a, the function values on that side approach L. So when I write, if you look in the subscript here, notice that I'm approaching a and there's a negative, seemingly superscript or power. That minus sign means that I'm approaching a from the left, or from values of x that are less than a. Okay, and then there's the same notion right here. Okay, this would be a right-hand limit, so the plus sign down here in the superscript means I'm approaching a on the x-axis, but this time from the right. And if I write the limit as x approaches a from the right of f of x equals L, that means the outputs are approaching L as I keep approaching a from the right side. Okay, so x values approach a from the right, the outputs are approaching L. And you just saw that in the previous example. I had a one-sided limit, and I had I did a left-hand limit and the function approached 3. I did the right-hand limit, the function also approached 3. And that leads me to the following theorem. That's just the notation. Okay, so a two-sided or normal limit exists. So for a two-sided limit to exist, the limit from the left and the limit from the right must exist and be equal. So I'm saying the limit equals L if and only if the right and left-hand limits are equal and also equal L. Okay, so example 2. So this time in example 2, I'm going to be looking at a piecewise function. Okay, so this, again, you might remember this from pre-calculus. A piecewise function is a function that has two different definitions on different parts of the domain. So for instance, the way f of x is computed, if I want to find an output, my input x is going to be plugged into 2x plus 1 for any input less than 2. And it's going to be 2x minus 2 for any x greater than or equal to 2. Okay, and you'll notice that my piecewise function has two different definitions, which, if you look at the graph, it's broken up into two different pieces. And the question is, does f have a limit at 2? And we're going to do this graphically. We're just going to do this graphically on this problem, and then I'll also show you how to do it numerically through a table. But you'll notice something different about this function and the previous function. The previous function, the graph looked like a line, and it was defined everywhere except for at 3, and there was a hole there. And it turns out that function has a limit everywhere, even at the place where there's a hole. Now this time, you'll notice that the function is just a line, except for there's a jump at positive 2. Okay, both lines have slope 2x, okay, but they have different y-intercepts. Okay, so the function's moving along from left to right until you get to positive 2, in case it jumps down. Okay, right at this point right here, it jumps down and it begins increasing again at positive 2. So I claim this function has a limit everywhere except at possibly positive 2. Now, notationally, what I'll do is, okay, I want to answer this question. Do I have a limit at 2? Well, the only way that you can have a limit is if the left-hand limit of the function and the right-hand limit of the function are equal to the same value. Now, look at the graph. As I approach 2 from the left, follow the graph. What are the y-coordinates approaching as my x-coordinate approaches 2 from the left? You'll notice that the graph would be approaching that open circle, which has a y-coordinate of positive 5. So the left-hand limit is 5. Okay, but now let's start looking at the right-hand limit. As I approach 2 from the right, and I follow the graph, the function values or y-coordinates are approaching. If you look on the x-axis here, if you look on the y-axis, the y-coordinates are approaching the value of 2. So the right-hand limit is positive 2. Okay, so those are different. Okay, so since the left-hand limit and the right-hand limit are not equal, let me actually rewrite this in one more time. So again, the limit as x approaches 2 from the left, saw that was equal to 5. Okay, and that is not equal to the limit as x approaches 2 from the right of f of x, which I believe we saw was 2. Okay, hence, if the left and right hand limit are not the same, the limit as x approaches 2 of f of x, okay, and again I'm just going to write D in E for does not exist. Okay, so the answer to the question up here is no. F does not have a limit at 2. Basically, what you're basically saying is at 2 the function is not behaving in a similar manner, right? Because on one side it's getting closer to 5. On the other side of 2 the function values or outputs are getting close to 2. The function does not have the same behavior on both sides, hence the limit does not exist. Okay, but the limit would exist everywhere else. Okay, so now I can come down here. Again, there's the notion of a left-hand limit. Okay, so first of all, a couple things I want to point out here. Yeah. So notice if x is less than 2, the piecewise function, it said, is really 2x plus 1. Now again, if you're going to make a table of function values, like if I was going to do this by hand, if I was going to approach 2 from the left, I'd probably do 1.9, 1.99, 1.999. Okay. And you'll notice when you plug in 1.9, you get 4.8. And you're going to get 4.98 when you plug in 1.999. And I believe you're going to see 4.998 if you plug x equals 1.999 in. So you'll notice that the function values as you approach 2 from the left are getting close to 5. Okay. Okay, but then you can do the right-hand limit. Now if x is greater than 2, f of x is really 2x. Oh shoot, was it minus? Hold on, I gotta go double check this. Erase all strokes. It's 2x minus 2. Okay, that's what I thought. Oh, I have it actually showing up. Alright, I should have looked right here. There's the 2x minus 2. Alright, x is less than 2. Okay, not less than, Chris. If x is greater than 2, f of x is 2x minus 2. If you make a table of function values, okay, this time if I want to get close to 2 on the right, I start with something to the right of 2, like 2.1. To make it get closer to 2, I just keep slipping zeros in between the decimal and 1. And that would be x approaching 2 from the right. And the function values are 2.2, 2.02, 2.002 would be the next one if you check. So if you approach 2 from the right, if x approaches 2 from the right, you're going to see that the function values are also decreasing and getting close to 2. So just like we saw from the graph, f approaches 5 on the left of 2, to the left of 2, and it approaches 2 to the right of 2. Okay, so left and right hand limit are different. The limit does not exist. Now I'm going to have to show you how to do these algebraically. I guess I could just show you right now before I even get to the algebra of limits in just a second. So usually if you have the expression for a function or the equation for a function, there's actually a way to just find the limit algebraically without having to make a table and without having to look at the graph. So, for instance, if I wanted to do that here, okay, and I was going to do two limits, like for instance, if I was going to approach 2 from the left, and I was, okay, so if I was doing the limit as I approach 2 from the left of f of x, okay, so I'm going to do this algebraically. I'm going to show you the rules in just a second. Okay, so if x is approaching 2 from the left and I want to find the limit, okay, so again, if I want to see if there's a limit at 2, especially with a piecewise function where it's broken up at 2, you would actually have to see if the left and right hand limit agree and have the same value first. Okay, so the limit as x approaches 2 from the left of f of x, I can actually replace f of x. If I'm approaching 2 from the left, right, you're going to notice that x is actually less than 2, and when x is less than 2, f of x is 2x plus 1. Now that's a polynomial, and we're going to see in just a second that when you do limits of polynomials, you just plug the limiting value of 2 in. Sorry, that should be a 1. So I plug 2 in for x, and you're going to notice that you get 5. Okay. Then we can do the right hand limit. You're going to notice that x is greater than or equal to 2 if you're approaching from the right. So the limit as x approaches 2 from the right of f of x, if look back at your definition of a piecewise function up here, if x is greater than or equal to 2, notice I'm rewriting all the limit notation, but I'm just replacing f of x with the expression 2x minus 2 here. That's a polynomial, it's a linear function. You can plug 2 in for x, which is going to give you 4 minus 2, which gives you 2. Okay, so you see the left-hand limit was 5, the right-hand limit was 2. This is a really bad 2 right here. Okay. And again, the limit at 2 does not exist then because the left and right-hand limits are different. Okay, so you can do that graphically, numerically, or algebraically. Okay, so I just did some limits algebraically. I guess we've actually done them in 3 ways. We've done limits by investigating them graphically, numerically, and then just simply using algebra and substitution. Now I'm going to go through the properties of limits that allow us to do the algebra of limits, so that we can do as many limits as possible without having to either investigate graphically or numerically with a table. Okay, so I'm going to go through all these properties of limits without justification. So let f and g be 2 functions, and assume that the limit as x approaches c of f of x equals L, and the limit as x approaches c of the function g of x equals k. Okay, and there is a typo here. Notice that this should probably say it should probably be m. Okay, so I should probably use L and m up there to stay consistent. Okay. Now, I'm going to probably justify a few of these. So, like, number one, the limit as x approaches c. Let me use purple, actually. Let me switch colors. The limit of a constant k as x approaches c. Okay, now think about this. Okay, think about this graphically. Here's the value k. If your function is a constant function and always has the value of k, and here's the x-axis, here's the y-axis, well, it doesn't matter where you are on the graph, right? It doesn't matter what x is approaching. The y-coordinates are always k. Okay, so the limit of a constant function is always going to be that constant k. Okay, the function does not change no matter what x is. If the function is always k, the function values are always approaching k. Okay, so that's that first one. Let me erase this. Okay, so now for number 2. Oops. So for number 2, probably didn't need that much room. Okay, now I'm calculating the second one. What's the limit as x approaches c of the function x over the function y equals x? Okay, well the function y equals x goes through the origin. Okay, and you can think about it this way. The limit as x approaches c of x is saying, what is x getting close to as x gets close to c? Right, so if this was c right here, and I look at this point on the graph, the y-coordinate is also c. Okay, well, again, let me grab some purple from the top. If I'm approaching c on the x-axis from left or right, okay, well, your function values or your outputs are the same as the inputs. Okay, so the limit of x as x approaches c, no surprise, is c. Right? If x is approaching c, x is approaching c. That's essentially what that is saying. Okay, so let me get through the rest of these rather quickly. I'm not going to again justify these, but these should be pretty straightforward. So the limit of a sum of functions, well, you can calculate the limit of each function first and then add. So that's basically distributing the limit operation or notation. So the limit of a sum is the sum of the limits. Okay, the next one also, the limit of a difference is the difference of the limits. Okay, so this one would have been L plus M. This one would be L minus M if I'm using the letters L and M. Okay. Now we've got 5 through 8. Okay, so I'm right here. Now, for this one, if you have the limit of a constant k times a function, turns out that you can just pull the k out front and then calculate the limit. So this would be KL. Okay, the limit of a product of functions. Okay, this one's a pretty nice property as well. Is, oops, it's the product of the limits, so that'd be L times M. the limit of a quotient. This one is pretty not surprising, is you can take the limit of the numerator divided by the limit of the denominator, but this only works when the limit as x approaches c of g of x is non-zero. And the last one is if you take the limit of an nth root, you can bring the limit symbol underneath the radical. So you can do the nth root of the limit of f of x first. Or you can do the limit of f of x first followed by the nth root. Okay. So these are all the properties of a limit that allow us to do all the algebra of limits. Okay. So let me show you how to. I'm going to show you how to use them, but I'm not really as picky about this all the time. So for instance, now if I'm going to look at example 3, if I was going to use the limit properties here, okay, say I want to do the limit as x approaches 2 of x squared plus 5x. Okay, now you're going to have to look up top to see which limit laws I'm applying. Okay, so first what I'm going to do is I'm going to break it up. X squared plus 5x is a sum of two functions, right? If I go back over here on the left, there's x squared and there's 5x. Okay, that's a sum of two functions. Essentially it's two terms. I can do the limit of the first term, x squared, plus the limit of the second term, 5x. Okay, now the first term, x squared, can be rewritten as x times x, a product of functions, plus, and then the second term I can pull 5 in front of the limit. Okay, so one of them I'm just rewriting x squared as a product, and then on the second limit what I did was, okay, there's basically a limit property that says any constant multiple can come out front. Okay, now the first term, you can break this up as a product of limits. I can do the limit as x approaches 2 of x times the limit as x approaches 2 of x plus 5 times the limit as x approaches 2 of x. Now I'm out of room. Probably should have written this smaller. Okay, but I'm just going to come up here and erase the top part. Okay. And if you look at the bottom now, okay, the limit as x approaches 2 of x, you saw up in the properties that that's just positive 2 times. Okay, then I have I'm multiplying that by the limit as x approaches 2 of x, which is again just 2, plus 5 times, and then the limit as x approaches 2 of x is again 2. 2 times 2 is 4, plus 5 times 2, which is 10. The limit ends up being 14. Okay. Now, there is just a better way. X squared plus 5x is a quadratic function, but it is a polynomial. So if you're actually doing the limit as x approaches 2 of x squared plus 5x, it actually turns out, and you'll notice, that if you just plug the limiting value of 2 in for x, you'll get 2 squared plus 5 times 2, which will also give you 14. So it turns out that the limit of a polynomial is the same as the value of the polynomial at the limiting value. So that's the next theorem. If you look at the next page, or just below, and so of limits of polynomial and rational functions. Okay, so number 1, the limit as x approaches c of f of x is just f of c if f is a polynomial. So you just plug the limiting value in. The limit as x approaches c of r of x, where r is a rational function, okay, as long as the denominator is non-zero at c, again, you can just plug c into the original function. Okay, as a matter of fact, for most of the functions that we study in this class, as long as the function is defined at a particular value, the limit will be the same thing, except for, of course, maybe like your odd functions like piecewise functions. But like polynomial functions, rational functions, radical functions, exponential functions, logarithmic functions, the limit will always just be the same as the function value. So things really don't oftentimes get weird. The only time limits get weird is where you're finding a limit at a value not in the domain of a function, or if you're finding limits of like piecewise functions. Okay, so let's do 4 limits here that are basically just pretty straightforward, using those two properties and the algebra of limits properties from before. Okay, so combining the theorems about polynomials and rationals with those algebra of limits, I can do this first limit. Okay, so if I want to do the limit as x approaches 2 of 3x cubed minus 2x plus 1, okay, what are you gonna notice first? You're gonna notice that this function is a polynomial, and if the function's a polynomial, you're just gonna plug the limiting value of 2 into the function, and you're gonna get, okay, 2 cubed is 8 times 3 is 24 minus 4 is 20 plus 1. I believe that limit would end up being 21. Okay, part B, the limit of a radical is the square root of the limit. Now, you don't actually have to do this. You could have just plugged -1 in again, but I'm just going to show you the process. You can pull the square root out front, and then you can plug the -1 in, because 2x squared plus 2 is a polynomial. Okay, so the limit ends up just being the square root of 2 times -1 squared plus 2, which ends up being the square root of 4, which is 2. Okay, and part C, okay, so this is a rational function, and for rational functions, what I suggest that you always do is, it's probably a good idea, it's not really necessary. Actually, you know what? I'm not actually going to do this. It says that if a rational function is defined at the limiting value, again, the limit is just going to be the value of the function itself. So you'll notice that x squared minus 20 is not 0 at 5. Okay, and this is a rational function. So you can just plug 5 in for x. Since you're not going to end up being dividing by 0, you get 15 over 25 minus 20, which is 5. That limit ends up being 3. Okay, so limits are actually not too difficult. You'll notice for these 3 functions, all you had to do is plug the limiting value in. Each one of these functions is defined at the limiting value, so you can just plug the limiting value in. Okay. Alright, so next example, I'm going to come back to a piecewise function. Okay. And I'm going to do 4 values here. Okay, so I'm going to do 4 limits. So part A, I'm going to do the limit as x approaches 5 from the left of f of x. So remember, for a piecewise function, if you're going to do this algebraically, actually let me work my way down. This is equal to the limit as x approaches 5 from the left. Now, if you come up here, if you're approaching 5 from the left, that means x is less than 5. So f of x is going to equal 2x plus 3, which is a polynomial. You're just going to plug the 5 into 2x plus 3. 5 times 2 is 10 plus 3 gives you 13. So the limit as the left-hand limit would be 5. Then you can do, okay, the limit as x approaches 5. You know what? It's already written there on the paper. Okay, this equals the limit as x approaches 5 from the right. Now, this time, if I'm approaching 5 from the right, x is bigger than 5, so f of x becomes minus x plus 12, which is a polynomial. You can plug in 5, and negative 5 plus 12 will give you positive 7. Okay, so now I know that let me rewrite that. Positive 7, I said. There we go. So the left-hand limit is 13, the right-hand limit is 7. You would see a jump in the graph if you graphed this piecewise function. What does that tell me about this limit? That means the regular limit does not exist. Okay, and finally, if I want to compute f of 5, if you look at both pieces of the domain for this piecewise function, neither of those pieces includes the number 5, right? That function's graph is 2x plus 3 to the left of, strictly to the left of 5. It's minus x plus 12 strictly to the right of 5. So f of 5 also does not exist. Okay. Finally, one more example. I'm trying to keep these videos under 60 minutes. There's the last couple weird situations where the functions are rational and aren't defined at the limiting value. Okay. So when I look at the first function and I'm trying to calculate a limit of, so I want the limit as x approaches 1 of this rational function, you'll notice it is not defined at positive 1. So I cannot just do direct substitution to calculate this limit. What I can do, however, is, and this is generally what you're going to do, if you can't plug the number in directly, you are going to hope that the numerator factors. Okay, so this function hopefully has a hole at positive 1, and the limit will still exist. Now, I think this has to factor as a minus 4 and a minus 1. So notice that the middle and outer terms, negative 4x minus 1x, give you minus 5x. X times x is x squared. Negative 4 times negative 1 is positive 4. Now, since x is never allowed to be 1, okay, you can cancel off those factors. You're left with the limit as x approaches 1 of x minus 4. One thing I want to mention is notice that as I am simplifying limits and writing equality signs, notice that as I'm doing my algebra, I am still writing the limit as x approaches 1 each time. The only time that that can go away is when you're actually computing a limit, not just simplifying algebra. Once I have simplified this function down to x minus 4, that's a polynomial, and it's defined at 1. Now the limit sign can go away when I plug in 1. The limit ends up being minus 3. Okay. It's interesting, if you think about this function graphically, at positive 1, oops, it's actually not what I want, hold on. If you think about this function graphically, at positive 1, there's actually a hole there. And I don't know what the graph does, I'd have to look at it, but okay. If you actually graph this in Desmos or some other graphing technology, you'll notice that at x equals 1 there is a hole in the graph, but the graph still approaches the same point on either side, and that point has a y-coordinate of negative 3. Okay, now part B is a little trickier. So part A, notice that this function is undefined at x equals 1, but the limit at x equals 1 exists. Okay, and we got -3. So the function doesn't exist at 1, but the limit did. Okay, I want to look at an example of a function where the function is not defined and does not exist. Okay, this one's a little trickier though, because it's a piecewise function. Now you're going to notice, okay, I'm going to call this f of x. And hopefully you're going to notice that there's an absolute value in this. So in certain times x plus 2 will be positive and the absolute value goes away and you just get x back. And this is actually when x is greater than or equal to -2. Or the absolute value of x plus 2, it can be minus x plus 2. And in that case, you would just get a minus x, right? The x plus 2's would cancel. And this happens when x is less than 2. Okay. So, since the actual function I'm trying to find the limit of is piecewise, and it depends on, it's piecewise, so it depends on if x is less than -2 or greater than -2. There's two different pieces of the graph. So if you want to know if the limit exists, you probably have to do the left and right hand limits. Okay, so the limit as x approaches -2 from the left of this function, f of x. Okay, so again, the function is actually just simplifies to x if x is greater than or equal to -2, and minus x if x is less than -2. So you actually have to calculate the limit at -2 by doing left and right hand limits. If you're doing the left hand limit, okay, we saw that if x is less than -2, f of x just becomes minus x. Okay, that's a polynomial. You can just plug the limiting value in, so that's minus -2, you'll get positive 2. Okay, but if you look at the limit as x approaches -2 from the right of f of x, f of x is just the same as positive x in that case. Okay, if you're approaching -2 from the right, you're in this situation. And now that x is a polynomial, you just plug -2 in. Okay, that becomes the right-hand limit. So what that means, since the left and right-hand limits are different, the limit as x approaches -2 of x times the absolute value of x plus 2 over x plus 2, this limit does not exist. Okay, so if you're ever finding the limit of a function with absolute value, you're going to have to see it as a piecewise function, and you're probably going to want to have to investigate the left and right hand limits to see if the limit exists. Now, we're clocked in at 63 minutes. I try not to make the videos this long. I had to do a little bit of algebra in this video. Thanks for tuning in, though. If you have questions, make sure you're calling my Google Voice number to get me directly on the phone, sending me emails. I can do Zoom conferences one-on-one for office hours. Thanks for tuning in. Let me know if you have questions. Bye.